Okay, now we're going to talk about the energy required, the heat energy required to change the state. And by changing a phase or a state, I'm talking about moving from a solid to a liquid or from a liquid to a gas. As you know, if you move from a solid to a liquid, it's called melting. If you move from a liquid to a gas, it's called boiling. Conversely, if you move from a liquid to a solid, it's called freezing. If you move from a gas to a liquid, it's called condensation or condensing. And energy is required to remove or put together those bonds that are necessary to make this change of state occur. And generally when the molecules are traveling at large distances, again, energy has to be put into place in order to bring those molecules together. And then if you want to pull them apart, you have to put energy in to pull them apart. And that energy can be measured. The measurement or the amount of energy necessary is different depending on the different substances. And this is called the latent heat coefficient. And it's called latent because the heat is hidden in terms of the fact that there's no temperature change while this while the heat is being absorbed by the material. And since there's no temperature change, then it is basically the mass times the latent heat coefficient. So here's an example of what happens. For example, if you take ice, and if you start over here, you see that as you put in heat into ice, that to raise its temperature from -20 to 0 takes a certain amount of heat, and that with each addition of heat, the temperature goes up until you reach 0 degrees, which is the melting point. Then you have to melt all the ice, and during that time, the temperature doesn't change, even though you have to put additional heat in order to melt the ice. Then the water's heated up again, and during this time it's water, and again there's no change in state, so you can see a temperature change coordinated with the change in heat that's being put in, and then it boils. And again it flattens out. There's no temperature change, but there's heat being put in. And then once it's converted all to steam, again you have a rise in temperature. Now, sublimation is something else that can occur, and that's when you change directly from a solid to a gas, and heat is also required to do that, and that's called the heat of sublimation. Now, when you solve problems related to this, you should take a very systematic approach to doing that. So you examine the system as a whole and determine if there is a temperature or phase change. Okay, there has to be either a temperature or a phase change in order for heat transfer to occur. And then you need to make sure you understand which direction, from what object to what object, the heat is being transferred. List all the objects that have temperature and or phase changes. Okay, you make sure you don't forget any, because that's commonly what causes mistakes. Identify exactly what needs to be found. What do you need to know? In other words, in the problems we talked about before, both those problems, what we wanted to know was the final temperature. And you have to know what you need to know in order to know how to set the problem up. You make a list of all the things you know, either that are stated directly or inferred by the way the problem is stated. If certain things are not given, but are usually one way or another, then you assume that those things are the way they are, if they're not the unknown that you're trying to find. For example, if the specific heat of water is not given, and you know that it's 1 kilocalorie per kilogram, then you can infer that and put it in. Then you set it up and solve the appropriate equation for the unknown. Then you put in known quantities into the equation and obtain the numerical solution, and make sure you get the units and significant figures correctly. And then you check your answer and see if it makes sense. So here's a problem. And again, I'm going to try with my limited capabilities here to see if I may just do one of these because it's been kind of difficult. But here's a problem. How much heat transfer is required to raise the temperature of this containing this much water from 30 degrees to the boiling point, then boil some of the water away? So there's two objects here. There's the pot and the water. And both of those have to be heated from 30 degrees to 100 degrees. Then the third portion of this is the boiling away of this much water. So you have three sections. You have the heating of the aluminum pot to 100 degrees, the heating of the water to 100 degrees, and then the boiling away of that much of the water. So if we look at that, you heat the pot, so that's MC delta T plus, and then you heat the water, MC delta T, and then you boil away a certain amount of water, so plus M heat of fusion. And so here will be 0.75, here will be 0.125, and delta T is from 30 to 100, so that's 70. So it's 70 times 0.125 times 0.75. Here is the mass of the water, which is 2.5 kilos times 1 times the same 70 degree temperature change. So those are those two factors. And then that you're going to boil away 0.75 times 539 kilocalories. And if you do the math here, you get an answer of 590. And I'm sorry, but I can't seem to get this to work very well. So the total here is 590. On this second problem, you have a 3.5 kilogram bag of ice, and notice this is kilojoules per kilogram. So when you multiply these two together, melting all this ice, you end up with kilojoules, okay? But you have to change to joules because a watt is a joule per second. So the average power in watts, if it takes 24 hours for all this ice to melt completely but stay water at 0 degrees, so there's just one factor here, the melting of the ice. So it's going to be 3.5 times 334, which is 1169 kilojoules, or 1.169 times 10 to the 6 joules. And that occurs over 24 hours, or 86,400 seconds. So if you divide 1.169 times 10 to the 6 by 86,400 seconds, you get 13. Now, we're going to move over to a different type of discussion. We're going to talk about the three common methods of heat transfer. The three common methods of heat transfer are conduction, convection, and radiation. And here's convection as well. Conduction is the transfer of heat through direct contact, which is pretty much what we've been talking about for the whole chapter so far. So when these logs are touching directly on this fireplace floor, there's heat transferred from the logs to this floor, and that's through direct contact. So that's conduction. Convection, on the other hand, is the transfer of heat through an intermediary, or through a medium, or through some sort of medium, I guess is the best word, carrier. And that's why it shows these air currents moving through. And the air currents that are moving the heat are called convection currents. So this air comes in, grabs the heat, and sends it up the chimney in the form of hot air. So you have the air is actually heated up, and there's no contact like in conduction, but the air itself, a convection oven circulates the air in such a way as to allow that air to transfer the heat around the whole oven. And then radiation is the transfer of heat through direct electromagnetic radiation. Remember that infrared is the heat spectrum, and so radiation can also lead to heat transfer. So when you're standing close to a fire, even if there's no air moving, even if you're not touching it, you can feel the heat off the fire, and that's radiation. So those are the three forms of heat transfer. In conduction, what you basically have is a hot object and a colder object, and the energy in the molecules is transferred through collision from the hotter object to the colder object. And so you basically have a high energy collision. This molecule, which is going slower, speeds up, and therefore its heat goes up. This one slows down as a result of the collision, and the heat is conducted in this direction. Now, heat conduction is always from the hotter material to the colder material, and there are three factors that are important. The first is what the material is made of, so it's heat conductivity. Secondly is the cross-sectional area of the contact, and the third is the distance between the two objects. And here's the formula for the rate of heat transfer is the heat over time. It's the rate of heat transfer is equal to this constant times the cross-sectional area times the distance times the difference in temperatures divided by the distance between the two. K here is called thermal conductivity, and it's the material's ability to conduct heat. And as you guys know, some things conduct a lot heat a lot better than other things. For example, when you put insulation in your house, the idea is to put something in there that does not conduct heat. And they actually measure that, and it's called the R factor. And the R factor is the conductivity divided by the distance. And it's a measure of a material's ability to act as an insulator. Convection, on the other hand, is the transfer of heat through the use of currents of air. So you have, or it can be other mediums. Water can be a convection medium. Air is a common convection medium. And what happens in a house is cold air sinks, hot air rises, and so the colder air comes through the furnace, hits, and it's heated up, and then the hotter air rises, and this circulation of air is what causes the room to warm up. Here's another example where now water is acting as the convection. And if you look inside at water when it's being heated up, frequently you'll see a shimmying, and that's the movement of the water. And if you stir water while it's being heated, it will heat up faster because you're using the water as a convection medium. The fur on an animal can act as an insulator, and the way it does that is it causes the air to stop, or does not allow it to move freely across the body of the animal, and it basically allows for a slowing down of the transfer of materials or heat from the inside to the outside by setting up all these small convection loops within the fur. The last method, as we said, was radiation. And radiation basically leads to the loss of heat in this situation. Heat comes in and hits this ice and causes it to melt. An ideal radiator, that is a material that gives off all of its heat, electromagnetic heat radiation that it has. So a material where all of its heat rate energy is given off in the form of electromagnetic radiation is called an ideal radiator. An ideal absorber is a material that absorbs all the electromagnetic radiation that falls on it. So here's a couple of situations. This first situation you have a black material which absorbs heat with very little reflected, and then if it's hot, it emits a lot of heat and very little is retained. And so a black object is both a good absorber and a good radiator. However, a white object, on the other hand, reflects most of its heat and absorbs very little, and retains most of its heat and reflects and emits very little. So it's a poor radiator and a poor absorber. Now there is an equation that can be used to calculate the radiation of heat, and it's called the Stefan-Boltzmann law. And this is the amount of heat per unit of time is equal to a constant known as the Stefan-Boltzmann constant, designated by sigma here, times the emittivity of a material, so that's materially based, times the cross-sectional area for radiation, times the temperature to the fourth power. And this emissivity is a measure of how well an object either radiates or absorbs. So this would have a low emissivity. And the greenhouse effect, just to let you know, is a situation where the Earth is warmed because the atmospheric gas absorbs infrared radiation, and it's re-irradiated in all directions and sends most of it back to the Earth. And so what happens is that the composition of the atmosphere determines whether electromagnetic radiation in the form of IR is allowed to escape or not. And if it's not allowed to escape, then it bounces back onto the Earth, and when it does that, that's known as the greenhouse effect. Now it's known as the greenhouse effect because that's how a greenhouse works. A greenhouse works because the windows, those panes of glass, reflect all the radiated heat from that passes in from the sun back inside and keeps the room warm. Now this is a summary, and this is the last slide, and it's a summary of how a thermos bottle works, and it takes advantage of all three of the concepts that we've talked about. So you have material here. The inside of the bottle is coated white, and remember, it's a bad absorber and a bad radiator, and so it will not absorb heat from the material, radiant heat from the material. So that's why it's coated silver or white. Then there's this gap here, and the gap is to prevent the flow of air. And by preventing the flow of air, it prevents convection currents from transferring heat out of the bottle. The third is this stopper and these little things that keep the inside bottle from touching the outside bottle, thus preventing conduction of heat from the inside to the outside. So this bottle right here summarizes how all three of the various things that can occur. So it inhibits radiation. The glass walls inhibit the radiation. The spring devices in the bottom and on the sides prevent conduction. And the vacuum, with the lack of air in here, prevents any convection currents. So I want to thank you for your time, and we'll see you in class next week.